This is part 5 of the molecular structure and bonding unit. And we saw from the previous part that valence bond theory doesn't handle the description of the bonding of polyatomic molecules very well. We need another explanation. And so we go to the last remaining theory that we're going to be looking at for this module, and that is molecular orbital theory. What is this molecular orbital theory? It's a more sophisticated model that can be applied to simple and complex molecules. It describes the bonding very well, okay? The Schrödinger equations from the quantum theory can also be written for molecular orbitals, and the approximate solutions for these Schrödinger equations can be constructed from what we call linear combination of atomic orbitals. Now, we've already seen a little bit of this when we talked about hybridization, but this theory gets everything right. So it applies to simple molecules, complex molecules, diatomics, and polyatomics. So what it does is it takes the sums and differences of the atomic wave functions, and this results in orbitals that are spread over the entire molecule. So let's go back to what we learned about the orbitals from the earlier work that we've done. Do you notice that the colors of the lobes of the orbitals are different? And they also now have a sign, okay? I showed this to you earlier, but this just indicates the positive and negative parts of the wave function. And this will only be evident with p orbitals where and d orbitals and f orbitals. In most instances, we don't get the sign of the wave function of an s orbital being negative. Okay, so how do we do this? So let's take a nice easy example to start off with. When we combine orbitals, the wave functions that have the same size are going to interfere constructively, and this is going to give us something called a bonding orbital. Okay, and when wave functions with opposite signs interfere, they're going to do so destructively, and we get something called an antibonding orbital. Now, I realize that sometimes this terminology can be confusing, because how can electrons sit in an antibonding orbital? Well, it just means that the orbitals are of higher energy because there's destructive interference. So let's have a look at the picture on the right-hand side of the slide. So let's have a look at this one at the top here. You will see you've got two orbitals. Both of them are s orbitals because they're spherical in nature, and you'll see that they both have a wave function. There are two wave functions above each of the orbitals. Now, when these two are added together, so we combine them in a linear fashion, so they overlap in a head-to-head nature, resulting in a single bond, okay, we get an equivalence of this orbital shape over here. And you will notice that for the graph that you see here, that the amplitude of the graph is obviously now added because the two waves have been added together. The wavelength is the same, but the amplitude has changed. All right, now let's have a look at an antibonding orbital. All right, so in this instance, we will get a wave function of an orbital with a different sign, okay? And if you see that, again, these two will overlap with one another, but they will destructively interfere with one another. What happens? It means that this part of the interaction is kind of wiped away because there's destructive interference. And what do we get? We get this orbital over here, which shows the two lobes being pushed away, and you get something here called a node or a nodal plane. So right in the center here is the node, okay? So there's the node, and then you get a nodal plane between the two orbitals where the electron or the shape of the orbital is now pushed. Most of the orbital sits as far away from the nodal plane as possible. Okay, so let's have a look at a simple example with hydrogen. As we did with valence bond theory, let's look now at hydrogen with molecular orbital theory. Again, it's a homonuclear diatomic molecule. Homonuclear means the same nucleus, the same type of atom. Diatomic means two atoms. So there are going to be two molecular orbitals. All right, and it's critical to remember this. Make a note of this somewhere, that the number of atomic orbitals that you have is going to equal the number of molecular orbitals that you're going to have. So the wave function is then given by this equation over here, where we have a bonding orbital and an antibonding orbital. Okay, in many instances, I'm going to show you the notation now. So the bonding orbital is lower in energy than the atomic orbital, while the antibonding orbital is higher in energy. Okay, so let's have a look at this diagram on the right-hand side of the slide, this diagram here. You will see that we have, in this case, if this was hydrogen, this would be a 1s orbital. Okay, so this is a 1s, and this would be a 1s orbital. Okay, but they are going to interact differently. Okay, so they're going to form the bonding orbital at the bottom here. Okay, and they're going to form the antibonding orbital at the top over here. All right, and we'll talk about the bonds in a little while, but generally what happens when we have head-to-head overlap, we're going to get a sigma bond. So this is going to be a sigma bonding orbital, and then this one over here is going to we're going to call it a sigma star orbital. It's an antibonding orbital. All right, so we're not going to use this convention of using the phi's. We're going to actually designate for the type of bond that is formed. All right, there is another possibility. Let's have a look at this picture down the bottom on the left here. All right, it is possible for an s orbital to overlap with a p orbital. And if there's no real interaction, we get something called a non-bonding orbital. Okay, it's the same energy as the initial atomic orbitals. So what happens here, you will see that this is the s orbital, the blue sphere that you see. And then, of course, you get the p orbitals, and we've designated them with different colors because the one indicates the positive part of the wave function and the other indicates the negative part of the wave function. And where you get overlap, okay, so you get the s orbital overlapping with the positive portion of the orbital, you get constructive interference, and when you get overlap with the negative part of the wave function, you get destructive interference. And in this instance, you get something called a non-bonding orbital because the interferences cancel out with one another. Okay, so now where does this notation of the molecular orbitals come from? Where does the pluses and minuses come from? Well, it comes from symmetry. Now, while I understand we've not dealt with symmetry just yet, we can still apply some simple explanations for these pluses or minuses. All right, so let's take a look now at sigma bonds. These orbitals are symmetric to what's called a C2 rotation. A C2 rotation is just a two-fold rotation about the bond axis, and there are no nodal planes in the z-axis. Now, we've defined a convention that says that the bonding axis is the z-axis. So in other words, if we get head-to-head overlap like we do over here in this drawing that you see here, this defines the fact that this is the z-axis, the z-axis. Okay, and in this case, if we take the center of this orbital and the center of this orbital, and we rotate this by 180 degrees. You can see this 180 degree rotation. If we rotate here by 180 degrees, then you see that the plus over here ends up being a plus over here. And this has a symbol which I will be explaining to you later. It's called a sigma G, and I'll tell you what the G stands for shortly. Okay, if the opposite is true, so in other words, we perform a 180 degree rotation, a twofold rotation, and the sign changes, then this becomes a sigma with a U underneath there. Okay, so in this case, you will see that here we've got overlap, which is head to head. So in this direction is the z-axis here. Okay, and again, this is a SS overlap, SP overlap along the bonding axis, and this is a PP overlap, head-to-head overlap along the Z-axis, like that. Okay, so let's talk about pi bonds now, okay? Again, we apply the same principle, okay? So the pi bonds, the orbital is going to change sign with a twofold rotation about the bond axis, okay? So remember now that this is where the bond axis is. Let me indicate that's the bond axis, okay? That's the Z-axis. Now what happens if I take this orbital, okay? Remember it's this part here, the plus and the minus, and I rotate it 180 degrees. If it changes sign, it's now called pi u, okay? But if it stays the same sign as it does in B of this diagram at the bottom here, then you'll see that it becomes pi g, okay? And remember that the bonding here is a sideways overlap. So there's sideways overlap here, and of course this pink line is the bond axis. And along the bond axis, we're now going to get a nodal plane where there is no indication of electron density along this black line. Okay, so these again, the top one, the top diagram over here is a bonding interaction. Okay, it's called a bonding interaction. And the bottom one down here that I've indicated already will be an antibonding pi interaction. Okay, so let's do a quick summary. Okay, a quick summary says that where there's a sigma bond, there is no nodal plane passing through the internuclear axis. So remember, this is the bonding axis. I'll draw it again. That's Z. There is no nodal plane. There is overlap. All right. And here is the bonding axis. Okay. And remember that the orbital itself has a nodal plane indicated by the dotted line. But remember, this is now in the direction of the bond, okay, so there's still no nodal plane. And similarly here, where we've got the Z-axis going in this direction, there are two nodal planes for the two p orbitals. They're perpendicular to the bonding axis because remember, the bonding axis takes place in this direction. Okay, so that is a sigma bond. With a pi bond, we have one nodal plane passing through the internuclear axis. Again, this is the Z-axis here, and we get sideways overlap over here and here. And then a delta bond is now an overlap between two d orbitals, where you get two nodal planes passing through the internuclear axes. All right, and it's become very complicated to see, but what I want you guys to notice is you can tell me and explain to me about the S and P orbitals that overlap to form sigma and pi bonds. All right, so now what does this G and U stand for? Okay, well, they are German words, and they talk about the orbitals that are symmetric to inversion. Okay, now inversion is something that we're going to look at in symmetry later on, but essentially what you need to remember is that if you do a rotation and you keep the sign the same, then remember I showed you earlier that you get this sigma G. Okay, the G stands for gerade. I'll pronounce it again, gerade. Some students say Gerard. No, it's a German word, gerade. Okay, so that means that the sign stays the same where there's a bonding interaction. If there is a change of sign, okay, or there's two different orbitals coming together with two different signs of the wave function, then we put the subscript U, and that is ungerade. Okay, ungerade. This is where the orbitals are unsymmetric to inversion. So in this case, you will see that for sigma bonds, when there's a bonding interaction, we get a sigma gerade, which is usually a bonding orbital, and when there's an anti-bonding interaction, we get an anti-bonding orbital called sigma ungerade. It's also, we label it sigma star so that we can indicate that it's an antibonding. Now with the pi orbitals or the pi overlap is different. Okay, so remember now, in this case, you need to look at the sign. So where we have a bonding orbital, you're going to see that the two pluses are going to sideways overlap like this and like this. But if we do the center of inversion here and we do the 180-degree rotation, we see that the sign changes. Okay, so there's the 180-degree rotation, right? And the sign changes. So because the sign changes, it now becomes a pi bonding ungerade. And then here with an anti-bonding overlap, okay, you can see that the 180-degree rotation, this gives you an anti-bonding interaction because the signs of the wave function is different. And we say there's the 180-degree rotation. Okay, the signs are the same. So this now becomes a pi star because it's anti-bonding, and it is gerade. If you can't remember, try to remember the simple principle that the sigma is generally bonding is G and antibonding is U, and then for the pi bonding it's swapped over. All right, so here is a full description of what the orbitals look like. So let's have a look at on the left-hand side for this particular S orbital overlap, which you've seen before. So now we've got two S orbitals with the same wave function. They give us the bonding, and because it's the same wave function, this becomes a sigma gerade. Okay, here at the bottom in the second diagram at the bottom on the left, we have two S orbitals with different signs for the wave function. That will give us an anti-bonding orbital. So then this one here will become a sigma ungerade, and we donate it with a star to say that it's anti-bonding. All right, what about the p orbitals now? Let's have a look at the p orbitals. Well, the pz is going to act head to head, okay, and therefore we're going to remember if we do a 180-degree rotation in this case, you're going to see this is a sigma, okay, so this one will be a sigma bond where you've got the overlap of the wave function. So this becomes a sigma, it's gerade, okay, because the wave functions overlapped properly. Okay, then on this side here, you're going to see that when we do the 180-degree rotation, so if I took this one and 180-degree rotation, I would end up with the blue over here and the orange over here, or the red over here. In this case, if I do the 180-degree rotation, I'm going to end up with the opposite sign. So this becomes an antibonding orbital. So this one will be sigma star ungerade. Okay, now let's have a look at the sideways overlap. Okay, the sideways overlap, I will explain this again in the next slide. If these become head to head, this is a pi bonding orbital, but remember if I do the 180-degree rotation, this one is blue at the bottom here, okay, and this one is red at the top here, 180-degree rotation. It's going to be ungerade, but it's bonding. And then this one at the bottom over here, when we do the 180-degree rotation, the blue is going to be the blue at the top, okay. So this becomes a pi star antibonding, but it's gerade. Okay, so that's how we classify the molecular orbitals. Let's just go a little bit further. Okay, how do we put the orbitals together? Well, we do a linear combination of the atomic orbitals. Okay, so what happens now is in this case, where we've got an s orbital at the bottom here and an s orbital at the bottom here, we got two atomic orbitals. We're going to get two molecular orbitals. Okay, so when there's a positive overlap, we're going to get a bonding interaction. It's a sigma bond. It's gerade because the signs of the wave function are both the same. And then we're going to get a second orbital, which is ungerade. It's a sigma star, which means it's antibonding. Two molecular orbitals. So here is one the second one, and we've got one and the second one here. Okay. Similarly for the p orbitals, we have 3 p orbitals and 3 p orbitals. That means we need to have a total of 6 molecular orbitals. All right. So we get one sigma Gerarda interaction, which is the pz interaction, because that is the head-to-head overlap. So we get one sigma g down the bottom here, and one sigma star ungerada at the top here. And then the remaining 2 orbitals are the px and the py. Doesn't matter which one, they are degenerate, which means they have the same energy. We have to write them on the same energy level. And when we overlap them first, we're going to get the pi ungerada, because that's the bonding orbital, and then the other 2 are the pi star Gerarda, which is the antibonding orbitals. And you'll see the energy. So the bonding orbitals, the bonding molecular orbitals, are lower in energy than the atomic orbitals, while the antibonding orbitals, this one and this one, are of higher energy than the corresponding atomic orbitals. Now, sometimes what happens is you get something called S and P separation, S and P mixing, I beg your pardon. So for a general molecular orbital diagram, if there is a large separation between S and P orbitals, then we assume that there's no orbital mixing, and then what happens is that we get the situation on the left-hand side here, where we can write the sigma orbital underneath the pi orbitals. Okay, so you can see that there is a separation here between the sigma and the pi orbitals. All right, but when the S and P separation is quite small, we get mixing, and therefore, if you have a look at on the right-hand side of the diagram, you'll see that the sigma and pi orbitals have swapped places. Okay, so it doesn't really affect down the bottom over here with the 2 s orbitals, but when we're talking about p orbitals, if the gap between the s and the p is quite small, we're going to get orbital mixing, and if the gap is relatively large, we won't get the orbital mixing at all. Okay, so we also don't draw too many lines because it becomes confusing. So we just need to make sure that we understand if there's S and P mixing, and I will explain when that occurs. Then we need to swap the orbitals around. All right, so here is the molecular orbital diagrams from helium all the way through to fluorine. Okay, now what I will do in a separate video is I will do 2 worked examples for nitrogen and for oxygen. Okay, and I'll show you exactly how we fill them and what happens between the 2 of them. Now, as you can see with nitrogen and oxygen, with nitrogen particularly, if you look over here, you can see that the gap between S and P is quite small. So here you're going to get mixing taking place. And suddenly with oxygen and with fluorine, the gap between the S and P is quite rather large, so we don't get mixing taking place. So in general, you will find that with boron, let me just change the pen quickly. So boron, carbon, and nitrogen, you end up with this sp mix. Okay, and then for oxygen and fluorine, there's usually no mixing. Okay, just for interest's sake, this is quite a complex diagram. You'll probably only deal with this in 3rd year, but I need to just give you a heads up so that you can see what happens. This is what happens when we form molecular orbitals from d orbitals. Okay, so Again, you also get end-to-end overlap, as you can see over here. There's end-to-end overlap, and here these orbitals will overlap in the same plane. This will give you pi overlap. Remember, it's sideways overlap, so there's the sideways overlap, there's the sideways overlap, and you will find that you've got the pi and the pi star orbitals. And then down here, when we've got sort of a really complicated mix of things, you're going to get the d and the d star orbitals, and it tells you the types of orbitals that are involved that will give you these orbitals. This is just for interest's sake. I really want you to understand what happens with materials that have s and p orbitals only. Okay, so as I mentioned earlier, when we fill a molecular orbital, we obey the same rules as if we were to fill an atomic orbital. Okay, so we obey Hund's rules, we use the Aufbau principle, the Pauli exclusion principles, all of those, we use those. Okay, so you first fill the bonding orbitals first, and then we fill the antibonding orbitals, and if there's more than one bonding or antibonding orbital, you fill them as if you would fill an atomic orbital. So just like with the p orbitals, you put one electron into each orbital and then you start to pair them up. You do exactly the same thing with the molecular orbitals. Now, if we have at the bottom left here, this diagram here, this one is for a homonuclear diatomic. Okay, so that means both atoms are the same. So for example, hydrogen. And when we form the molecule, they are of equal energies. So therefore, we draw the orbitals on the same energy level. Now remember that these are molecular orbital diagrams. This is actually a diagram of energy. Okay, so the increasing energy goes up like this. So we have to draw the energy level, the energy of the atomic orbitals on the same level. All right, and then we know that the bonding orbital, which is down here, is of lower energy, and the antibonding orbital at the top here is of higher energy. Okay, now we will see what these energies are when we look at the next part. All right, if the two atoms are unequal, their energies are going to be unequal, and we need to represent it as such. So as you can see, in this case, we have unequal energies, and we see that the one atomic orbital is higher energy and the second atom is of lower energy, and so they're represented accordingly. And sometimes they are very unequal. So if we look at this diagram on the right hand side here, the energies are very, very unequal, and that will be most likely when we have two very significantly different electronegative atoms occurring.